Hello, guys. Welcome back to Maison African Motives. Still on power machines and five, working on question papers and revisions. In this case, we've got question number 5 of April 2016, which is on governors. That is a Porter governor. So we are given in our question, that's question 5. A Porter governor is a sleeve mass of 6 kgs. Okay. Remember, guys, I told you that the sleeve mass is simply the dead load in this case. That is, we are given the mass of the sleeve, which is M. That's your capital letter M. So you can just take our information. Whilst the rotating balls each have a mass of 1,8 kgs, the arms of the governor are 330 millimeters long, and they form an angle of 30 degrees to the vertical. The coefficient of friction between the sleeve and its shaft is 0.33, and the minimum and maximum radii of rotation is 130 millimeters and 210 millimeters respectively. Calculate the following. All right, so this is the information that you're given in this case. All right, so let's just save our data down. So you said we've got the mass of the sleeve in this case, which is our dead load or dead central load mass, which is our capital letter M, that is 6 kgs. Okay, also we are given that whilst it's rotating, whilst the rotating balls, they have a mass of 1,8 kg. So the rotating balls, they've got the small letter M. So that is for the rotating balls, which is M. That is 1,8 kilograms. Okay, so this is for the balls, the rotating balls. Okay, so that is rotating balls. And this is for the sleeve. That is, we are dealing with what? The dead central load. Okay, so let's check the other information. We are also given that the arms of the governor are 330 millimeters long. So we can refer to this as L. Okay, I'm going to just have a sketch of the diagram on how you can just have an information what is happening on this information that you're given. All right, so that's in meters. We can divide by 1,000, which is 0.33 meters, since a meter is equivalent to 1,000 millimeters. So this is 1,000 millimeters, or just milli means times 10 to the exponent of -3. All right, so you can multiply by 10 to the power of -3. And they form an angle of 30 degrees to the vertical. This angle is formed between the arms and the vertical, which is 30 degrees. So that's our theta of 30 degrees. In this case, we're given theta 30 degrees. Also, we are given that here the angle formed, okay, then the coefficient of friction between the sleeve and its shaft is 0.33. That is the coefficient of friction, which is written, we can just write it, coefficient of friction, remember from your engineering science there. Okay, so remember, from the coefficient of friction, this helps us to calculate the frictional force. Okay, remember, from your engineering science, we say the frictional force can be calculated from the coefficient of friction, because you are given coefficient of friction times the normal reaction, or the weight component in this case, which is mass times the gravitational acceleration. So you're going to have the coefficient of friction times the mass times the gravitational acceleration to represent the weight component, which is going to be 0.33 for the coefficient of friction times the mass of we are using. Okay, sorry for this one, because this is let's take to the information. Let's get to the information. We are given the coefficient of between the sleeve, okay, between the sleeves, which means we are working with the mass of the sleeve in this case, between the sleeve. All right, so let me indicate this properly so that we do not confuse with this M. So we are going to use capital letter M. Why? This is between the sleeve, which means we are working with the sleeve mass of 6 kgs. So we are going to multiply times 6 kgs times the gravitational acceleration of 9,1, so 9,81. So this can give us the frictional force, which is going to be 19,4238. So that's something like 19,424. All right, the 8 is going to change the 3 into 4. That is in newtons. So which means we can obtain the frictional force, which means there is a friction that is occurring in this case. All right. We are also given the radii, which is the radius of each, the minimum and the maximum, respectively, 130 and 210. So these are the radii that you are given. That is, we can just write them separately. So we are given R1. We can just refer R1 as our minimum, which is 130 millimeters to meters. We divide by 1,000, or we multiply by 10 to the exponent of -3. That's 0.13 in meters. And R2, which is our maximum, that was 210 millimeters. So we also convert or divide by 1,000, which is 0.21 in meters. All right, so this is what we are going to have in meters. So in this case, we have, this is your minimum, this is your maximum. What is the use of all this information? Okay, the question is, from this information that we have, calculate the following. That is the minimum speed limit in revs per minute and the maximum speed limit in revs per minute. Okay, so that is, we are to calculate N1 and N2 in revs per minute. If it was in rad per second, we calculate omega-1 and omega-2. But this is going to limit us still because we do not have a formula that has got direct N from our Porter governor. So which means we can calculate W1 and W2, which means the ones that you are going to calculate omega-1 and omega-2. Remember, I told you guys that there's a relationship between the omega and the N, which is in revs per minute, and the omega in rad per second. Let me just write the relationship before we put the diagram and we do the calculation. Remember that omega is equivalent to 2 pi n over 60, provided that this n is in revs per minute. You shall obtain your omega in rad per second. So by manipulating this formula, if you are to cross multiply 60 times this, we are going to have 60 omega, which is equal to 2 pi n. So we can divide by 2 pi to obtain n. So that means our n is equivalent to 60 omega over 2 pi, which is measured in revs per minute. So n will be in revs per minute. So these two, they are very, very important to know the conversion from the omega to N1 and the conversion from N to omega. This is very, very, very important in our calculation. So in this case, since we are to calculate N1 and N2, it means there is a need for us to calculate omega-1 and omega-2. But how can we calculate omega-1 and omega-2? Okay, we understand that from our Porter governor. Okay, let me have a sketch. I had a sketch before, but let me just have a sketch because it's going to help us to calculate some of the other things here. Okay, before the sketch, we understand that from the mass of the balls and the mass of the sleeve in this case, these two, they have a great relationship in terms of the weight calculation. That is, when we are given the frictional force, okay, remember I said we can use this formula where we had the mass of the rotating balls plus the mass of the sleeve times gravitational acceleration, all this part being equivalent to the mass of the balls times omega squared times the height. Okay, so from this consideration that we have, whenever there is a frictional force, take note, guys. Here we have a frictional force on this question. There is a frictional force that is operating. So on this weight component that we have, where there is a combination of the balls and the sleeve, we are going to subtract the frictional force that is between the sleeve, because this is on the sleeve. So this, we are going to subtract the frictional force now. So this is the difference that we are going to have on the normal formula that we had before and this one. So since we are to focus on calculating omega, so that the omega is going to give us n, we can use this formula direct, or we can make omega the subject in this case. By making omega the subject, what can we do? We can divide both sides by mh. So we can divide each part here by mh. So this can cancel. We remain with omega squared, which is equal to this. So to determine the value of omega now, you introduce the square root because there is a square. So this is going to be the square root of everything that we have on the right-hand side. So meaning to say, we are going to have the mass of the rotating balls plus the mass of the sleeve times gravitational acceleration minus the frictional force, everything over the mass of the balls times the height. So the h that we have determines the omega. That's why we have to calculate N1 and N2. So meaning to say, if we are calculating omega 1, we shall have this as omega 1, this as H1. Okay, if we are to calculate omega 2, that means we shall have our formula in the same way, but just written as omega 2. So it is going to be omega 2 is equal to the square root of the mass plus the mass of the sleeve minus, in this case, our frictional force, everything over the mass of the balls times the height 2. So this would be H2. So if we are to check, on the information, we have the mass of the balls, the rotating balls. In this case, we have got this mass. We have the mass of the sleeve. We have got the gravitational acceleration. We have got the frictional force, everything we have, but we do not have this H1. We do not have this H2. So that is where we are stuck, and we have to calculate H1 and H2. All right. So how are we going to calculate H1 and H2? These ones, we can calculate them. Remember the diagram that I referred to previously. If you are dealing with, let me just have our diagram. We have got an angle of 30 degrees. We have got the radius. We are given radius 1 and radius 2. So these two can help us calculate the height, and also with the involvement of the length of the arms. We are given the length of the arms in this case. So this can help us to calculate H1. Okay, so let me show you on the diagram, but this one we can even calculate it direct, but just because having our diagram in a basic way can help us understand. Okay, a Porter governor is actually of this nature. This is just a sketch for calculations, not the actual diagram, but the sketch that you can use for your calculations. Okay, so this is what we have. So we are going to have here, this is the ball. So we are going to have the rotating ball in this case connected to another one, in this case. Then we've got our sleeve in this case here. So this is where you have your sleeve. So you can join to this point like this. All right. So this is that sleeve bag. Okay. So from this point here, we are representing the height in this case, and this is to the horizontal, to the sleeve. Okay. Then we have got our radius in this case. So the radius that we are given, it corresponds also to the radius from this point again. So in this case, we are given two radii, the minimum radius and the maximum, which is R2. So we are given these values, we are given them R1 and R2, which means we can work with the radius 1 and the length of the sleeve. This is your sleeve here, and the angle, we are given the angle here, that there's an angle of what? Of 30 degrees. The length of the arms, which is 0.33 meters. Okay, so this is your angle here, your angle between, so the angle is between the arm and the vertical line. This is the arm, this is the vertical line. So you've got an angle of 30 degrees here. But I said previously that these two lines, they are the same. They are vertical lines, which means they are parallel. They will never meet. So this angle and this angle, they will be equal from your alternate angles or Z angles. You are creating a Z in this case. So these two angles, they are equal. And this, we are at 90 degrees. We are given the length of the arm, that is 0.33. So we are given this length of the arm, which is 0.33 meters, with the angle of 30 degrees. So we can use the angle that we are given in this case to calculate the side, that is this one. But since we are limited now to the radius, say our radius is supposed to be, we are limited that these radius, our R1 and our R2, which means this diagram here, I'm going to take this length and this radius, okay? So that we can calculate the height. This is the height. So this height here is determined according to the first radius or the second, if you are given 2 radii. So that is that is the condition or the use of these radius, the maximum and the minimum and the maximum. They are going to help you to calculate the value of h. Since I said here, you need h1 and h2. So this sketch, we are going to see that it is going to be reduced. We can reduce it this way. I just want to focus on this triangle. There are so many things that we have got here, but I just want to focus with the most important part for now. So this is what we can take from our diagram. All right, the right angle triangle with our length, which is of the sleeve of 0.33, and the radius. So if we are referring to R1, we shall calculate H1. So R1 goes with H1. So the first radius that we are given was 0.13. That is the minimum here. The minimum radius is 0.13. So we are going to use 0.13, okay? So that's 0.13. So we are going to take 0.13. So with these two, we can calculate H. From your Pythagoras theorem, L squared is equal to H1 squared plus R1 squared. That is RH plus R. So you can substitute H 0.3, or you can make even R1 the sub, depending with what you want, or you can even substitute, okay? L here, that's 0.33 squared is equal to H1 squared plus R1 squared, which is 0.13. So you can transpose this to the other side, which is 0.33 squared minus 0.13 squared is equal to H1 squared. It was adding, so it is going to subtract. So to find H1, you can introduce the square root both sides. So H1 is equal to the square root of this, which is going to give us 0.303, and so on and so on, and so this ones and so forth. So it's going to be 0.303 in meters, because we used the L here in meters, the radius in meters, which means our H1 is going to be also in meters. All right, so that means we can calculate our omega-1. Then we can calculate speed 1. Remember, here I'm referring to condition of these two as the two questions, the minimum speed and the maximum speed. I'm referring to these two at the same time. So if we are to calculate the minimum speed, that is, we focus with H1, we finish with this H1. We go to the maximum speed, we focus with H2 when this is maximum, when the radius is maximum. So that is what we have. So from minimum radius, we are going to calculate the minimum speed, which is N1. But remember, I said N1 is taken from omega-1. So that's why we need this H1 so that we can calculate omega-1. So with this H1 that we are given, let's check our H1 here. So we can take our H1 and substitute into the formula. So that means omega-1 is going to be equivalent to the square root of, that is the mass of the rotating balls, which is in this case, we are given the mass of the rotating balls. That was 1.8. So that was 1.8. Sorry. So we are going to substitute 1.8 in this case. All right. So this is 1.8 plus the mass of the sleeve, of which the mass of the sleeve is 6. So this is 6, okay, times the gravitational acceleration of 9.81. So we are going to multiply the gravitational acceleration of 9.81. Remember, because of the frictional force, we have to subtract now this frictional force, which is minus 19.424. So the difference between this question and the other question that we had is that we were not having the frictional force. This time, there is an involvement of frictional force. So to calculate omega-1, we subtract, okay, everything over the mass of the rotating balls, which is this one that we got at 1.8, which is the same, these two, they are the same, times H1. So H1, we are using the height now that we calculated here. So remember, H1, we got 0.303. So that's 0.303. All right, so we're going to have here 0.303. So this is your omega-1, which is measured in rad per second. Remember, omega speed, rad per second. So this is going to give us 10,23146 and so on, which is 10,231. That is in rad per second. So the omega that we have here in rad per second is the one that we are going to convert back to the revs, because the speed is needed in revs. And I said we can calculate n here in revs per minute from 60 omega over 2 pi. So we're going to use this formula to calculate n, since we have got the speed now. So it means our n from the formula, we say that is 60 omega over 2 pi. So you can substitute the omega that we got, which means if you are calculating any one, you use omega 1. So this is going to be 60 times omega 1, which is 10,231, everything over 2 pi. So this is going to give us N1 in revs per minute. Or you can substitute direct on the formula for omega 2 pi n over 60. Then you can just make any direct from there. You can substitute, then you cross multiply it, but still you get the same answer in revs per minute. So this is going to give us N1 in revs per minute. So we are going to obtain 97,6988, which is 97,699. The 8 is going to change another 8 into 9. That is in revs per minute, or you can write it as RPM, revs per minute, still one and the same thing. So in order for you to calculate the minimum speed N1, you used R1 to calculate H1, which was important for us to calculate omega 1. That was the most important part of the question, to say H1 in this case is helping us to calculate omega 1. So the same thing, in order for us to calculate the second part, which is the 5.2, where we are calculating the maximum speed, we are going to use H2. So meaning to say we are going back to the same diagram that we had before this one, and now we are to calculate H2. All right, so for 5.2, it means we have to calculate H2 so that we can use our omega 2 from this formula. So we need N2 in this case. All right, so we are going to start with H2. So as we saw that from this formula, H1 is simply affected by R1, which is the minimum radius. So we are going to use R2 now as to calculate H2. So meaning to say, if we are to calculate H2, we are going to use R2 in this case, of which our R2 is the maximum radius that we are given, which was 0.21 from the given information in meters. So since we saw that from the formula, we saw that this H2 is going to be equal to the square root of L squared minus R2 squared. That is from our Pythagoras. We can make this the subject, since we said L2 is equal to H2 squared plus R2 squared. So you can transpose L2 minus R2 squared is equal to H2 squared, then square root both sides, we obtain this. So this we can obtain our H2, which is the height affecting the omega 2. So we are going to have as the square root of L, the sleeve, the arms, sorry, the length of the arms, which is 0.33 squared, minus our radius 2, that's 0.21 squared. So this is going to give us H2. Okay, so we can calculate this value. We can determine our solution, which is 0.254 and so on, which is going to be 0.255 if you round off to 3 decimal places. So H2 is helping us to calculate omega 2 as we stated from this formula. So which means we are going to rewrite this formula for omega 2 here. We said this one for omega 2. So this is the one that we are going to use now to calculate H2, and we calculate our N2. All right, so I'm going to take down the formula. So we said in this case, from our formula now to calculate omega 2, our formula was given by the square root of the mass of the balls plus the mass of the sleeve times gravitational acceleration minus the frictional force over the mass of the balls times H2. All right. With the whole information given, that means we can calculate our omega 2. That is the mass of the balls plus the mass. So everything is going to remain as it is from this formula that we had here. All right, we wrote this part previously, these values here. Everything is going to remain as it is from this formula here. Only the height has changed. So here we are going to have 1,8 plus this value, which is 6 times the gravitational acceleration 9,81 minus the frictional force, everything as it is 19,424. Then we divide by the mass of the balls, which is 1,8 as it is, but multiplied to H2 now. So our H2 is the one that we calculated here. So this is where we are just having a difference. All right, so we can calculate our omega 2 in this case. We are just going to substitute our H2 in this case, which is 0,255. So having our omega 2 in this case in rad per second. So take note, it's going to give us omega in rad per second. So that is your omega 2, which is going to be 11,1529 and so forth, which is going to be 153 in rad per second. Then the question is not on omega. The question is on calculating the speed in revs per minute. So remember the conversion that we talked about to say n is equal to 60 omega over 2 pi from that conversion, or we can take it from omega, which is equal to 2 pi over 2 pi n over 60. So you can take it from any part. You can substitute here, then make then calculate any from the formula, or we can just make any the subject, then we can substitute now the values that we are given. Since we are to calculate any 2, this will be omega 2. So that means any 2, which is our maximum speed, is at 60 times omega 2, which is 11,153 times 2 pi. So this is going to be 2 pi. So by doing this, you are obtaining any measured in revs per minute. All right, so this is going to be your n in revs per minute. So therefore, our n in revs per minute, which is the maximum speed that we are given from the information, is going to be 106,50330, which is 503 to 3 decimal places. So that's revs per minute, or you can write it as RPM, revs per minute. So that's how we can attempt these typical questions. So as you can see, the Porter governor, or these governors, some we need to apply our mathematical skills calculations there on Pythagoras theorem, the issue of trigonometrical ratios, so that we can calculate any side, since there is an involvement of the height. But what was important in this case, all right, what was important in this case is this part here, the involvement of the maximum and minimum that is affected from the maximum and minimum height, which is given, which was taken from the radius. So there is this part, and also the use of the frictional force from this part, especially this part that I want you to see here, the involvement of the frictional force. Once there's a frictional force, you subtract both. Normally, your omega is supposed to be given as omega is equal to the square root of m plus m into g, like this, everything over m. If you make omega the subject from this formula, if you are not given the frictional force, you end up with omega this way. But because there is a frictional force that we subtracted, that is now we are having the involvement of that frictional force here, which is going to be affecting our answers to calculate omega 1 and to calculate omega 2. So these are the typical questions that you must expect to be asked on your typical exams for a Porter governor. So you just need to revise more questions from our past exam papers so that we can see how to attempt these typical questions. So that's it for now from Maison African Motives. Till we meet again.